Today we're going to take a look at the introduction to circles, and with circles, by a lot of definitions you can see here by the front page of your notes. Rather than have you copy down 5 different slides of circles definitions, instead I decided to copy them onto the page for you. It would take about the entire period really to copy all those notes down. A circle is a set of all points in a plane that are equidistant from a given point called the center of the circle. Now the key part here is the fact that it's in a plane, and as a result of that, circles are two-dimensional in shape. The distance from the center to a point on a circle is the radius of the circle, and two circles are congruent if they have the same radius. Okay, so if the same length from the distance to the edge of the circle is the same, your circles are congruent. The distance across the circle through its center is called the diameter of the circle. Meanwhile, those also apply into parts of a circle as well, because the radius is a segment whose endpoints are the center of the circle and a point on the circle. Chords are segments whose endpoints are points on the circle. So they go across the circle, but they have their beginning and ending points both lying on the circle. A secant is a line that intersects a circle on 2 points. And when we get to the segment or the circle picture, you're going to see the difference between a secant and a chord. Secants are lines where chords are instead segments. And finally, within this slide, a diameter is a chord that passes through the center of the circle. A tangent is a line in the plane of a circle that intersects a circle in exactly 1 point. It hits the edge of the circle and it bounces off. Coplanar circles that intersect on 1 point are called tangent circles, and when coplanar circles have a common center, they're called concentric circles. A line or segment that is tangent to two coplanar circles is called a common tangent, and there'll be different types of common tangents, common internal and common external tangents, and we'll show you what those look like here in a little bit. The interior of a circle consists of the points that are inside of a circle. The exterior of a circle consists of the points that are outside, and then obviously you have the circle itself. The point at which a tangent line intersects a circle to which it is tangent is called the point of tangency, and that's going to lead us to some theorems. Okay, theorem 10.1, if a line is drawn tangent to a circle, it's perpendicular to the radius drawn at the point of tangency, and theorem 10.2 is its converse. In a plane, if a line is perpendicular to the radius of a circle, at the endpoint on the circle, the line is tangent to the circle. In other words, tangent lines are perpendicular to the diameter at the point of tangency. And if two segments from the same exterior point are tangent to a circle, then those points are congruent as well. Both of those theorems we're going to take a look at here at the very end of the presentation after we deal with the parts of a circle. This is an example of an end-of-course test question that deals with the definitions as it pertains to circles. Kyle defines a circle as a set of all points equidistant from a given point. We want to explain why Kyle's definition is not precise enough. This really kind of leads you into a difference between two-dimensional shape and multiple dimension shape. Because in a three-dimensional shape, you still could have a set of all points equidistant from the given point. Kyle's definition is not precise enough because it needs to mention the fact that a circle is a plane figure. And as a result, all Kyle needed to say was, in a plane. Okay, and had Kyle said that, that makes the definition way more precise, because now you're limiting it to a two-dimensional shape. Looking on at parts of a circle. Okay, you have a circle here with a center O. And you can take a look at the different pieces and parts that we have to our circle. We're going to start with our radius. And the radius we're going to do in red, because that is the radius. Okay, there are several different radii of the circle. Okay, we have a segment from A to O. We have a segment from J to O, from I to O, O to G, and O to E. Each one of those red segments coming from O are radii of the circle. Similarly, okay, for blue, we're going to use the diameter. In the picture that we have, there's only one diameter of the circle, and that is a segment from J to E. It passes through O, but that is the only diameter of the circle that we have in this picture. Additional things that we have within this picture that we need to use. Okay, I'm going to write this in yellow. I'm going to write it up here in red. But our yellow lines are our chords. Okay, and our chords are segments whose endpoints lie in a circle. AC is a chord. C to G is a chord. D to G is a chord. C to D is a chord. J to E is a chord. Other chords, A to I. Okay, those I believe are all the chords of the circle there that we've highlighted in yellow. Now, chords are segments whose endpoints begin and end on a circle, but there's also a secant of the circle. Now, our secant we're going to do here in purple. Okay, there's one secant in the circle, and it is the line from B to C. Speaking of which, the segment from B to C is a chord. Okay, the line from B to C is our only secant in our circle. And then lastly, our tangent lines, and there are two tangent lines, and we're going to do those in orange. Our tangent lines intersect the circle and bounce off. Okay, the line from K through F, the line through H. Those are examples of tangent lines. Tangent lines are kind of important. If you guys have ever seen the movie Apollo 13, it was one of the big key issues. Once they tried to stir their oxygen tanks up in space, they ran into an issue because of the fact that when they had done that stirring, they blew up part of the ship. And as a result, they weren't sure if they got blown off course enough that they weren't sure if they were going to be able to hit the atmosphere at a tangent line, which would cause them to bounce off into outer space, or if they were going to actually land through the atmosphere using a secant. All right, so parts of a circle. Okay, moving on down through your page. We want to use the term that best describes the given line or segment, and our first one is TU. Okay, segment TU is a radius. Our next one, segment QS. Okay, QS is a chord. Line QT. Okay, QT's line is a secant, and it's kind of important that it's got this arrows on the end because that indicates that you have a line and not a chord. And then lastly, line PR. Okay, PR is a tangent. Okay, it intersects the circle at one point and bounces off. Okay, we want to tell whether the line, ray, or segment is best described as a radius, a chord, a diameter, a secant, or a tangent of circle C. Segment AC is a what? Okay, segment AC is a radius. What about segment AB? AB is a diameter. Okay, it's a chord that runs through the center of the circle and crosses our chord. What about ray DE? Okay, DE is a tangent. And lastly, line AE. Okay, line AE, and it's significant again that it's a line, is a secant. Are there any questions or no's? All right, the next several pictures that you see here are examples of some of the definitions. The first one up here is a set of concentric circles. Concentric circles have a common center, but different radii, and they extend out. And we're going to take a look at some pictures here that explain how these things apply in different settings in just a second. Our next set of circles that we have are externally tangent circles because they intersect in the outside of both circles, and as a result, they're externally tangent. And our last set of circles down here are internally tangent circles because they intersect on the insides of the circles. All right, so these are different examples that we have, and then these are what the properties can look like in different spaces. The first one here on the left side, most of you have seen a target before at different points in time. Targets, the circles inside of the target represent concentric circles. Dartboards would be another example of this. When you drop something in water, okay, it creates a ripple effect of circular waves coming out from where you dropped something. Okay, and as a result, those are concentric circles. And a crosscut of wood on a perfectly circular tree, like the pine tree that's been cut here, is an example again of concentric circles. So the crosscut of wood can have the same concentric circles as well. More tangent circles that are externally tangent. Okay, a big roll of toilet paper or paper towels. Those are examples of externally tangent circles. And also two coins that touch on the outsides of the coins are examples of externally tangent circles. Internal tangent circles, you can see here we've got a candle with a jar on the left-hand side. Okay, this is your example of the common internal tangents. The two dishes here create an example of an illusion of internally tangent circles. And you can see the tree there on the right-hand side on the pot that the tree is actually growing in versus the wicker basket that decorates around the outside of it. Those would give you an example of internally tangent circles as well. Now, there also are tangent lines that can be common lines. Okay, this is an example of a common internal tangent. And a common internal tangent is a tangent line to multiple circles that pass between the centers of the circles. Okay, so since this line here passes in between the center of the circles, it's a common internal tangent. Now, similarly, you can also have a common external tangent that passes along the outside edge of the circle. Okay, so this is a common external tangent. Okay, two tangent lines hitting along the edge. Now, you've seen common external tangents before. Most of you at some point in time have taken a pencil and put it up against two round objects, like the two coins in this picture. And this is an example of a common external tangent. And this picture here, the wrought iron fence and the gate on that wrought iron fence, actually gives us both types of internal tangents, or both types of tangents. My common internal tangent I'm going to highlight here in yellow. Okay, and it is the vertical poles in between the centers of the circles up here in our line. Okay, so those will all be examples of common internal tangents. But where we run into an issue, though, also is you do have a common external tangent that runs across the top of each of these circles and also one across the bottom. Okay, so the orange is a common external tangents, and our yellow lines are our common internals. Some other properties of circles that we need to be prepared for. The radius of circle C is given. We want to find our diameter of circle C. If our radius is 13, what's your diameter going to be? Okay, it's going to be 26. Because remember that a radius is half the length of the diameter. And if our radius is 3.2 inches, our diameter will be 6.4. Okay, questions on that? The centers of two circles are given here in a picture. Okay, and the circles are P and Q. Our radius for circle P is 8. The radius of circle Q is 12. We want to find each distance. First of all, if we know that the radius of circle P is 8, we want to probably start filling in a little bit on that. Okay, which means that RP is going to be 8, PS is going to be 8. Now, similarly, the radius of circle Q is 12. So what does the length from S to Q have to be? Okay, it's going to be 12 minus 8, so that's going to give me a value of 4. Now, once we've got that done, we're going to be able to find our distance from R to Q. Because our diameter of circle P is 16, and the distance from S to Q is 4, as a result, RQ will be 20. And the distance all the way across from R to T will be 32. Are there any questions there on that one? Okay, tangent lines are perpendicular to a radius at its point of tangency. Okay, so we want to tell whether AB is tangent to circle C. And if it is, angle A has to be a right angle. In order for that to happen, you have to create a Pythagorean theorem triangle. So the question that we're asking here is 18 squared plus 80 squared equal to 82 squared. What's the relationship? Okay, well 18 times 18 is 324. 80 times 80 is 6,400. And combined, those two add up to 6,724. Now, doing the same thing, if we were to take 82 and square that, 82 squared would be what? Okay, it's also 6,724. So is AB tangent to circle C? The answer to that question is yes. Okay, moving on. Same kind of problem. This time it asks us to find the radius of a circle. Well, again, in order for us to have a radius of the circle, we have to create a right triangle. So r squared plus 12 squared has to equal 13 squared in order for that to be a radius. Okay, 12 squared is 144, 13 squared is 169. You subtract 144 from both sides, r squared is 25. And when we take the square root of 25, we find our radius to be 5. So remember that tangent lines are perpendicular to radius at a point of tangency. Now, that leads us to this problem here. And this time we're going to have to do a little bit of work with quadratic equations in order to get through this problem. Because in our diagram, point B is a point of tangency, and we want to find the radius r of circle C. Now, at first glance, this doesn't look like it's too bad until you have to go through the methods to solve our problem. Because we know that AC is the hypotenuse of our circle. And since AC is our hypotenuse, then what we know is that r squared plus 80 squared has to equal our hypotenuse squared, but our hypotenuse is r plus 50. So now we're going to have to work through multiplying out r plus 50. Okay, well, 80 squared we know to be 6,400 because we've dealt with that earlier on. But r plus 50. Remember that when you have r plus 50, that is the same when you square that as having r plus 50 times r plus 50, and you have to use the FOIL method to solve this. Now the FOIL method truly is a distributive property. So if I take r times r, because that's my first two terms, that is going to give me r squared. Now, the rest of the FOIL method incorporates multiplying my two outside terms together. Well, that's r times 50. So that's 50r. Then we have to multiply my two inside terms together. And you can see that highlighted there in red. Well, that's 50r as well. And then finally, we have to take and multiply our last terms together. Okay, so that's 50 and 50. If we take 50 and 50 and multiply that together, that gives us 2,500. Now, when we simplify our problem down, we have r squared plus 100r plus 2,500. When I go to subtract r squared from both sides, guess what? They cancel out. So sometimes when you get a squared term within a problem, it will stay as a problem that you can solve as a linear equation because your r's will cancel out. And you'll see that happen several times during the course of this unit. My r's actually cancel, or r squareds cancel. Now, from there, we're going to subtract 2,500 from both sides. Okay, well, 6,400 minus 2,500 is 3,900, and that equals 100r. When you divide by 100, you find out that r is 39. So just because you get an r squared term within a problem doesn't mean that you need to panic, resort to a quadratic formula, or anything like that. Because sometimes those things will actually cancel out when you look at both sides of your equation. Tangent lines or tangent segments drawn from the same point to different tangent points are equidistant, which means segment AB, segment AD have the same length. Now, because you have the 10 and the x minus 3, and the 10 is outside of the x minus 3, you have to distribute across. And I'm just going to write that problem up as that. So 5x plus 5 equals 10 times x, which is 10x, and 10 times 3, which is minus 30. So 5x plus 5 is going to equal 10x minus 30. Okay, take your smaller x to your bigger x, we subtract 5x, and we'll add 30 back to the other side as well at the same time. That lets 35 equal 5x, and that means that x is going to be 7. Okay, are there any questions on that one? Now, not all problems are going to look like that. Some of them will end up being linear equations where you don't have to deal with any distributive property. For example, in this case, RS and RT are both tangents drawn to circle C from point R. And as a result, the distance from R to T and the distance from R to S are the same. Therefore, 3x plus 4 is going to equal 28. We'll subtract 4 from both sides, so 3x is 24, and that means that x will be 8. Okay, and again, if you plug that in, you can check your work to make sure that it does work out. Questions there? And then the last slide, when you use coordinates to describe each point or line, we want to name the coordinates of the center of each circle. Okay, so letter A. What are our coordinates for A? Okay, A is at 3, 3. What about B? Okay, B is the point 7, 3. Okay, name the coordinates of the intersection of our two circles. And those two circles intersect right here at this point. And that point is what? Okay, 0.63. Now, if you're to draw a tangent line between our two circles, the only tangent line that we have is that vertical line that passes through that point of intersection. So what is the equation for that line? Okay, since it's a vertical line, it's x equals, and that is 6 units away from the y-axis. The last question asks us for the radius of circle A. Our radius of circle A is what? Okay, it's 3. My diameter for circle A is going to be what? 6, because remember that your diameter is twice your radius length. Similarly, our radius for B is what? Okay, it's 1, and then our diameter for B is what? Okay, that one's 2. Are there any questions on any of this? Okay, we'll go ahead and pass out the homework then at this point.